It's the last Mathcounts mini of the year, and as you can see, we have some geometry. But what you don't see is Harvey, because I got this one all by myself. Now here we go. I have a triangle here. We're trying to find the largest possible area of a rectangle that's inscribed inside this triangle. Now by inscribed, we mean that all four vertices of the rectangle are on the perimeter of the triangle. So for example, you could put a couple of vertices down here, build a rectangle just like that. In fact, since there are four vertices of the rectangle, three sides of the triangle, we know we have to put two vertices of the rectangle on the same side of the triangle. So there's the ones kind of like that. But why don't we put two vertices over there and go this way? It doesn't seem like we can quite. Oh, the triangle looks like the triangle's obtuse. Well, we can see that it's obtuse by seeing that 10 squared is 100, 17 squared is 289. Add those together, you get 389. 389 is less than 21 squared, which is 441. So that tells us that this angle up here is indeed obtuse. So if we tried to make a rectangle by starting with two vertices over here, well, that's not going to work because this side's going to run away from us. And that's no good. But well, we're going to stay here. We know we can build a rectangle by putting two vertices down here, build a rectangle like that. And well, now we don't have to worry about putting two over there or two over here. But what if this triangle were acute? We then have to solve the problem 3 times. Fortunately, it's obtuse, so we don't have to worry about that, but I'd like you to think about that at the end of the problem, after we finish solving it, because maybe we wouldn't have to worry about it after all. But here we go. Obtuse triangle, 2 of the vertices are down here. One's over there, one's over there. Make a little rectangle. Now, before I start building the rectangle that I think is the largest one, or putting in variables, trying to solve some wacky equations, get a little intuition for the problem. What kind of rectangles can we fit in here? Well, I can start off by making a really tall and skinny one. I'm going to draw a little piece there. Tall, skinny rectangle. I can make this skinnier and skinnier and skinnier by moving these closer and closer and closer together. So we can get this side to go all the way down to almost 0, which makes the area of the rectangle almost 0. 0 is small. Now, we can then make it bigger, 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 bigger. Bring the height smaller, but we're going to make the width wider and wider, wider. Until, somewhere in the middle maybe, it'll get to its largest point. I'm guessing. It's just intuition, and guessing has a long and glorious history in mathematics. We're going to stick with our guessing for a little bit longer. When we get up to this point now, if we keep going, make the rectangle shorter and shorter and shorter, we're going to get to a point something like this, where the rectangle's really, really, really long, but really, 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 really short. And we can make it as short as we want to. We can make it almost 0, which will make the area of the rectangle almost 0. So this range of rectangles we can make, it looks like we start from something that's almost 0, and we can get bigger and bigger and bigger and bigger up to a point, and then we get smaller and smaller and smaller and smaller and go back to almost 0. Again, we're still just guessing. It could be that we get bigger for a while, then smaller, then bigger, then smaller, then bigger, and then smaller, 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 back to 0. But it just feels right that we go from 0 to big, back to 0 again. Now, if we do go from 0 to big and back to 0 again, where's big? Where's biggest? Because that's what we're interested in. Well, 0 to biggest and back to 0 again. I'm going to guess that biggest is right in the middle. Kind of just feels right. This kind of feels quadratic to me. It just feels like the answer is going to be just right smack in the middle. Well, guessing does have a long history, glorious history in mathematics, but that's because we back up our guessing, our intuition with proof. And that's what we're going to try to do now. Let's see what happens when we hit our guess. When this rectangle is exactly half the height of the triangle. Well, first let's figure out what the area of the rectangle is relative to the area of the whole triangle. And because this is half the height of the whole triangle, we know the height of this rectangle, we'll call it h over 2. H is the height of the whole thing. Well, if this is halfway up, I can see that this triangle up here is similar to this triangle here, because this is parallel to this. We're halfway up. This is the other half of the height. Tells us that the sides of this triangle are half the sides of the big triangle. So if our base is 21, this side up here is half the base. So the area of our rectangle now is this times this is base times height divided by 4. And that's really exciting, because the area of the whole triangle is base times height divided by 2. So now our rectangle that we get when we make it half the height of the whole triangle, its area is half the area of the whole triangle. And that's pretty cool. That makes me think we're probably right, because half is a really cool answer. Half is a really cool answer. It tells me, hey, there must be a beautiful reason. There must be a very elegant reason that the largest possible rectangle, boom, is this one right here. Now, we could find some inelegant reasons. You know, we could use our similar triangles here, throw up some variables, build a quadratic, complete the square. Yeah, I lost you. When I said complete the square, you're like, oh, I don't want to do that. So let's find the beautiful solution instead. You can go back and complete the square later. If you love you some algebra, complete the square all day long. That's great. It'll work. But I'm going to draw a picture because I like thinking in pictures. I'm going to draw a picture to prove why this is the rectangle we want. Actually, I'm going to draw a number of pictures, but we'll start with just one. We'll start with that rectangle that's right in the middle. And we just saw that its area of this rectangle, when it's right halfway, half the height of the whole triangle, its area is half the whole triangle. That tells us these three triangles out here, these other three triangles, they add up to the other half of the area of the big triangle. So that means the area of these three triangles out here, those three areas added up equals the area of this rectangle. So maybe we can take these three pieces, reassemble them, and make this rectangle. That would be cool. And here's a natural way to do that. I'm going to take these two triangles out here, I'm just going to flip them. Flip them over the sides of the rectangle. Because I know that this side of the rectangle is half the base, so these two pieces out here together make the other half of the base. So when I flip them over, boom, they're going to meet. Where it's nice that these are right angles, I know this triangle, boom, it's going to land, this side's going to go right onto this side. This one's going to come right here, they're going to meet right along the base. Now, this triangle that's left here looks an awful lot like this triangle up here. Maybe they're congruent. Let's see if they are. This angle right here, well, we want to see if this angle equals that angle. Well, this angle up here equals this angle down here because of these parallel lines. Now check out these two angles. Are they the same? Well, this angle's 90 minus that one. This angle's 90 degrees minus that one. And these two angles are the same because this triangle is just this one flipped over the side. So these two angles are the same. That means these two angles are the same. And this angle is the same as this angle. So that tells me that these two angles indeed are congruent. Same thing over here. These two angles, they're congruent. This side is itself. So sure enough, this triangle up here is congruent to this one down here by a little angle side angle. Congruence, this triangle folds in, fits there nice and snug. So sure enough, these three triangles can be assembled to make this rectangle. So the areas of these three equals the area of that rectangle. Now we just proved something that we already knew. We already knew that the area of this rectangle, half the area of the whole triangle. But what we don't know yet is that that's the largest one that we can build. Now let's see why that's true. We did this nice little folding thing when this rectangle had half the height of the whole triangle. Let's see what happens when we pull off that folding thing when our rectangle's a little bit taller or a little bit shorter. We'll try a little bit taller first. A little bit taller. We'll try the same folding thing. Now, rectangle's a little bit taller. That means this side is a little bit shorter than half the base of the triangle. So when I fold these over, these two pieces here are a little bit more than half this base. That means these two pieces here are a little bit more than this base of the rectangle. So when I fold them over, they're going to overlap. Fold them over. And they overlap just a little bit. Have a little overlap there. Now, what happens with this triangle up here? When I fold it down, it still fits right in here. Because this angle still equals this angle. This angle still equals that angle. This angle equals this angle. So these two angles are equal. These two angles are equal. Once again, this triangle is congruent to that one. Folds in right there. Nice and neat. So look what happens when I do my folding trick. I fold this triangle over. We completely cover the rectangle. There's a little bit extra. So that means the areas of these three triangles together is greater than the area of the rectangle. That means these three triangles together have to be more than half the whole triangle. Because when we take all the triangles, three triangles together plus the rectangle, we get the whole large triangle. So that means that this rectangle here, when we make the rectangle more than half the height of our triangle, its area is less than half the area of the whole triangle. But what happens when we make a rectangle a little bit shorter than halfway? Well, if it's shorter than halfway, that means the other side of the rectangle here is more than half the base of the whole triangle, which means these two pieces out here together are less than half, so we fold those over. They're not going to quite reach. They're going to fall a little bit short. So now when we fold this piece down, it's going to have to go outside the rectangle. Fold this in, still this angle equals this angle equals this angle. I can fold it right in here. And now once again, when I folded the three triangles over, I completely covered the rectangle, but there's some extra here. It goes out beyond the rectangles. That tells me the areas of these three triangles once again. Add them all up, you get something larger than the area of the rectangle. That tells me these three triangles together have more than half the area of the whole large triangle, so the rectangle has less than half once again. So we'll recap. When we're just nice, perfect, half the height here, the rectangle has half the area of the whole triangle. If we go a little bit taller, then the rectangle has less than half the area of the whole triangle. If we go a little bit shorter, the rectangle has less than half the area of the whole triangle. So now we've proved our intuition. The best we can do right in the middle. And we even already know how to find the area of that rectangle. We already figured out that it's half the area of the whole triangle. We have the base already. All we have to do is find the height of this triangle, and we're finished with the problem. And we haven't written down any fancy algebra yet. We haven't completed any squares. We're on to this. Uh-oh. How are we going to get the height? Okay. Now I'm stuck. Now, I'm trying to find this height here. I can use my little number sense here. I can see the 10 out here and the 17 out there and say, hey, I know some right triangles that might fit here. 6, 8, 10. 15, 8, 17. You know my Pythagorean triples? Sure enough, 6 and 15 make 21. All right, that's really nice. And then you're finished with the problem. It does work, but what happens if you don't see that? If you don't remember your Pythagorean triples? Well, now it's time for some algebra. And here's how this algebra goes. So we got our height there. We'll drop in the x right there for this piece, and 21 minus x over here. And now I have two right triangles. I can break out the Pythagorean theorem. It's one of the reasons we love right triangles. Use the Pythagorean theorem over here. We get x squared plus h squared equals 10 squared, which is 100. Then the same thing, we're going to use Pythagorean theorem over there. Yikes, we got 21 minus x, that whole quantity squared, plus h squared equals 17 squared, which we're going to call 289. And now we can just subtract. We subtract this equation from that one, because that'll eliminate the h, and we'll just be left with the x. We have 21 minus x, that quantity squared, minus this x squared, equals 289. Minus 100 is 189. Now I could use my difference of squares factorization to simplify this. So where I can just multiply this out, let's go ahead and multiply it out. 21 squared is 441. Minus 2 times 21 is 42 times x plus x squared minus x squared, and that's convenient. We no longer have a quadratic. That makes me happy. This is 189. And these two cancel out nicely, and we're left with negative 42x equals negative, yikes, 189 minus 441. That looks like 252 to me. And sure enough, divide by 42. Divide by negative 42, we get x is 6. So this is 6. Sure enough, this is 8. This is 15. 6 and 15 is 21, and all is good, and we're ready to answer the problem. Our height is h is 8. The base is 21. 21 times 8 is 168. So the area of the whole triangle here is half that. That's 84. And our rectangle here has half the area of the whole triangle. Half of 84 is 42. And that's a great answer. Whew. That's a wrap for this year, man. Yeah, thanks, Harvey. Thanks for letting me take that one, because, you know, the kids, they're starting to believe that I don't know any geometry, and, you know, yeah, thanks for letting me take the credit, yeah. Next year. Is that thing still on?